Hello everyone, and welcome back to C++ Real-Time Audio Programming with Bela. We've been working through the basics of synths and audio effects in the C++ programming language, and today we are going to look at circular buffers which we can use to implement delays and delay-based audio effects. In the course of this lecture, you'll learn how to keep track of previous audio samples in your code. We'll learn why circular buffers are a useful way to do this and how we can implement it. We'll also learn how to create delay effects on this basis. By the end of this lecture, you'll make an adjustable delay and also a simple echo effect based on a delay with feedback. The companion materials are available on GitHub. You can find the link on the bottom of the screen or in the video description. Before we go on, for anyone watching these lectures as they're coming out, I'd like to get your feedback on how they're going so far. In the video description, there's a link to a short survey, which you can fill out anonymously, or if you want to give us your email address, you can be entered into a prize drawing. More on this in the video description text. To run the code in this lecture, you'll need either a Bela starter kit or a Bela mini starter kit. You won't need any additional materials in this lecture, though some other lectures use breadboards and other electronic components. Before we get into the details of circular buffering, I want to review a couple topics. We have in previous lectures talked about the way that real-time audio is processed in blocks. As audio arrives at the input, it's gathered together into an array or buffer. That buffer is passed into our render function while the next buffer fills up. When we finished our audio computations, that buffer goes to the hardware to play back. Meanwhile, we're working on the next buffer. What that means is that at any given time, there are three things going on. Our input hardware is gathering audio samples into a buffer, our render function is processing a buffer, and our audio output hardware is playing back a buffer. This structure tells us that our latency eight audio input and audio output is equal to twice the buffer length plus any additional latency introduced by our audio processing code. In Lecture 8 of this series, we looked at how to implement digital filters. We started with a very simple example of the first-order difference, where the current output is equal to the current input minus the previous input. We made a block diagram for this filter, and we worked out what its coefficients would be, which is b0 is equal to 1, and b1 is equal to minus 1. We could therefore simplify our general diagram for an FIR filter to look something more like this. The challenge of Lecture 8 was turning block diagrams like this into working code. We had to figure out what information we needed to keep track of in order to implement this filter. The main thing we needed to save was the previous value of x of n, in other words, x of n minus 1. The way we approached this was to store that value inside a global variable, so that we always remembered it from one call to render to the next. Our code for this simple filter looked something like this. The variable gLastSample is declared as a global variable at the top of the file. Its function is to hold the value of x of n minus 1. The reason that it actually does hold x of n minus 1 has to do with this line inside of the render function. After we've done our output computation, we set gLastSample equal to the current input. The reason that we do that is that the next time around the for loop, gLastSample will then become the previous input, which we can use in our computation. Let's take a slightly more complex case where we use two previous inputs rather than just one. In this case, we'll need two global variables to hold the previous two samples. Let's call them, for example, gLastSample1 and gLastSample2. As before, we're going to need to update these variables at the end of the loop, something like this, where if in represents x of n, gLastSample1 represents x of n minus 1, and gLastSample2 is equal to x of n minus 2, then once we've finished our computation, we should move gLastSample1 into gLastSample2, and after that we should move into gLastSample1. Now the order here is extremely important. We had to move gLastSample1 to gLastSample2 before we could do the other move. We talked about the reason for this in Lecture 8, and it is essentially about avoiding overwriting any of the previous samples inadvertently. Our code implementing this structure will look something like this. After we've done the calculation for out, then we set gLastSample2 is equal to gLastSample1, and gLastSample1 is equal to in. Now suppose instead that we had a filter that only used x of n minus 2 and not x of n minus 1. The question is, do we still need gLastSample1 in this code? The answer is yes, we do need gLastSample1, because the only way we're going to remember x of n minus 2 is to remember all the samples that came before that, and this extends to an arbitrary number of previous inputs. On that note, let's suppose that we had a long FIR filter that needed the 100 previous samples of x of n. We know that we need to remember all 100 previous values, and we could in principle declare 100 variables to do that. Of course, this is a terribly messy way to go about this problem. What might we do instead? A better plan would be to use an array to hold the previous samples. We could declare an array of length 100, and we could store within it each of the previous values of x of n. And the mapping that we could use is as follows. G last samples of k corresponds to the expression x of n minus 1 minus k. So in this case, G last samples of 0 corresponds to x of n minus 1, G last samples of 1 corresponds to x of n minus 2, and so forth. On this basis, how would we find the value of x of n minus 100? This would be stored in G last samples of 99. Or, conversely, what value of x is stored inside of G last samples of 37? In this case, it's x of n minus 38. What then do we find in G last samples of 100? This one is a trick question. There is no G last samples of 100. This is an array that has 100 elements in total, so the only valid indices are between 0 and 99. A brief task for now, then, is to write some pseudocode. You don't need Bela for this, just write it down in a text editor somewhere. Write some pseudocode that saves the last 100 samples of x inside of an array so that you can implement the equation y of n is equal to x of n minus 100. Pause the video here briefly and try that. Here's my suggested approach to achieving this. We can declare an array G last samples, which has 100 elements in it. We initialize the array to 0 at the beginning of the program. Within our render function, we'll have our usual for loop that counts across the number of audio frames. We'll gather our input somehow, it doesn't really matter where it's coming from, and we're going to gather our output from G last samples of 99, which, as you'll recall, corresponds to x of n minus 100. The key part is the nested for loop inside of the outer for loop. You can see this for loop involving the variable called I, which counts downward from 99 to 0. The direction of counting is quite important here because we need to make sure that we're not overwriting any of the elements of the array. Notice also that we're stopping before I strictly reaches 0. Why is that? Well, if we tried to run this code with I is equal to 0, then we would access G last samples of minus 1, which of course is not a valid index of the array, and we could get a segmentation fault in our code. Now, this code is perfectly functional to save the last 100 samples of the input, but there's a drawback. What might that be? Well, the drawback has to do with its incredible inefficiency. Here's why. What we're doing is every time we get a new input sample, we are moving all of the last samples in the G last samples buffer. And this, of course, is not a good idea, because for every new input we get, we have to move 23 samples in order to add 1. But still, we're getting closer to some workable code. What should we do instead, then, to avoid this problem of moving samples around? This takes us to the topic of our lecture today, which is circular buffering. The term circular buffer is basically just a way of describing an array where we never move any of the samples inside of it. Instead, the only thing that moves is the pointer that tells us where we're storing and reading our values. What we'll do is every time we have a new sample, we will write that sample to the buffer at a location given by the write pointer. We'll then update the write pointer to a new location without ever moving any of the other samples. Before we get into the details of how this works, let's go back to the early lectures and talk about how we read from buffers in general. Recall that we would use an array as well as a read pointer which kept track of which index we were looking at any given time. The buffer and the read pointer were both typically global variables, and the read pointer would move as we played samples from the buffer, like this. We saw when we first looked at this that one of the trickiest things about working with this code was keeping track of the different buffers and the different indices and remembering what each of them means. In this case, we'd have two different buffers to work with. One holds the recorded sound and might be quite long. The other one would be for the real-time audio block, which would be the length of the block size of the system. What we needed to also do was keep track of two different indices. One kept track of where we were playing in the source buffer, which is what we call our read pointer, and the other kept track of where we were writing in the output for this particular call to render. We saw that this gave rise to a structure like this, where the read pointer would advance together with the variable called n inside of our render function. Once we got to the end of the first render function, the read pointer would carry on advancing, but n would reset to 0 for the next call to render, and we would copy another block of samples into our output buffer like this. And this process could repeat indefinitely until we got to the end of the recorded sound buffer. For more details on this, see Lecture 3. But back now to the circular buffer. A circular buffer is not so different from the memory buffers that we saw before. The main difference is in the way that we treat it, which causes it to act like a loop. What we'll do is write each new sample to the next location pointed to by the right pointer from the beginning to the end of the buffer. When we reach the end of the buffer, we'll wrap the right pointer around back to the beginning and carry on writing. In this way, the buffer always ends up holding the n most recent samples of our input, and the only thing we need to keep track of is where we are writing at any given time. That will tell us where we can find the remainder of the samples. So, suppose, for example, that we had a buffer of 24 samples and we had read the first 24 samples of x and stored them in this buffer. Now we receive the 25th sample, x of 24. This sample is going to be stored at the location pointed to by the right pointer, where it's going to overwrite the oldest sample in the buffer, x of 0. We then advance the right pointer by one slot, such that when x of 25 comes in, we can once again erase the oldest sample of the buffer and replace it with x of 25. We increment the right pointer again, overwriting the oldest sample once again, and we can carry on like this indefinitely. Notice, therefore, that at any given time we always have the 24 newest samples of x of n, and we are always overwriting the oldest ones as new ones come in. Here's a different geometric view on exactly the same system, which might be a little bit more intuitive to follow. In this case, I've virtually wrapped the buffer around to look like a kind of donut. This emphasizes the fact that the beginning and the end of the array are not special in any way. There's no such thing as the beginning or end of a circular buffer. There's only the most recent sample pointed to by the right pointer, and all of the samples stored before that. When we look at the buffer this way, we see that we can always find earlier samples by moving counterclockwise from the location pointed to by the right pointer. And, as before, when we receive a new sample at the input, we're going to overwrite the oldest sample, which is what the right pointer points to. So in this case, x of 0 is replaced with x of 24, the right pointer advances, x of 1 is replaced with x of 25, the right pointer advances, x of 2 is replaced with x of 26, and so forth. And again, this buffer is always holding the n most recent samples, but each individual sample has never moved until it's eventually overwritten 24 samples later. So what do we need to implement a circular buffer as code? Initially, it looks quite similar to the way we dealt with regular buffers. We need an array of memory, which might be a standard C array, or it might be a C++ vector. And we need a right pointer, which is essentially an int telling us which index of the array we're pointing to at any given time. We ought to declare both of those as global variables at the top of our file, and we should initialize the right pointer to some sensible value like 0. If we're using a C++ vector, we'll also need to allocate it inside of setup to ensure that we have enough memory available to us. Once we've done that, then inside of our render function, whenever we have a new sample, we can store it at the location in the array pointed to by the right pointer. Once we've stored the sample, we can increment the right pointer. There's one more thing that we need to do to make this a circular buffer. What's that? We need to keep the right pointer always within a valid range of the buffer. So, after we've incremented the right pointer, we check whether it's greater than or equal to the length of the buffer. Here you can see I'm using the method for the C++ vector class called size. When the right pointer reaches the length of the buffer, then we reset it to 0 so that the next samples are stored again starting from the earliest part of memory. Again, I want to emphasize that the beginning and the end of the region of memory have no special significance in a circular buffer. To tell what represents the earliest sample or the latest sample, we have to look with respect to the right pointer. This brings us around to the first of several Bela coding tasks for this lecture. In this task, I want you to implement a half-second delay using the template project called Circular Buffer. This code is set up so that the input signal is written to the left channel and the output signal is written to the right channel so that it's very easy to hear if the delay is taking place or not. You're going to need to do several things in order to implement this code. You'll need to declare the variables for your circular buffer, and you'll need to allocate it to hold a half second of audio. See the resize method of the C++ vector object for more details. You'll need to initialize your right pointer to 0 or some other sensible place. Then, once you get inside of render, you'll need to also store samples in the buffer as they come in, overriding the oldest sample in the buffer. Once you've stored a sample, then as we saw, you need to move the right pointer and ensure that it wraps around when it reaches the end of the array. A possibly helpful hint for this example is that you actually only need one pointer to implement this code. The reason for that is that the right pointer is always going to be pointing to the very oldest sample in your buffer. So if your buffer is only a half a second long, you can use it to get the oldest sample as well as overwriting it with the newest sample. Pause the video here and see if you can make this half-second delay work as expected. Here's an overview of the most salient bits of the delay code. You can see at the top of the file are two global variables, including the C++ vector, and you can see that inside of setup we use the resize method to store a half-second of audio. It's useful to call resize inside of setup because this lets us handle any possible audio sample rate. Inside of render, we start by reading the input somehow. I've grayed that out because it's not important where the audio input comes from. The audio output is the part that's important. Here we're reading the output from the delay buffer at the right pointer. The reason that we do this at the right pointer is as we discussed on the previous slide. The right pointer holds the oldest sample in the buffer, which is about to be overwritten. If our buffer is exactly half a second long, that's therefore a sample that's a half a second old. Once we've gathered the sample called out, we can safely overwrite the contents of the circular buffer with our input. We then advance the right pointer, checking if it's reached the end of the buffer. If it's reached the end of the buffer, we reset it to 0. Finally, we write the input and the output to different channels so that we can hear the difference between them. Okay, here we are now in context. In addition to the code we looked at a minute ago, we also have the file player object, which we saw in a previous lecture. You can find that in these files called monofileplayer.h and monofileplayer.cpp. Inside of setup, we're loading the audio file, which is a part of this project directory. We print some information once we've loaded it to confirm its size. This line is extremely important where we allocate the delay buffer to be a half a second long in audio samples. Then down inside of render we have the code we saw a minute ago. The first thing we do is gather the sample out of the delay buffer at the right pointer, and then right after that overwrite the buffer at the right pointer with our current input sample. We increment the pointer, wrapping it around, and we write the output to our left and right channels. We can run this code now and hear it in action. Alright, pretty clear, half-second delay. Now let's see if we can make this code more flexible. Where we're going with this is to see if we can change the amount of delay without having to resize the buffer to be exactly the right length. To see how to do that, let's address a couple questions. Let's suppose, for purpose of illustration, that we had a buffer that was 100 samples long, and we wanted to know what index was 2 samples older than gdelay buffer of 51. What's the answer here? Well, remember that we have to look counterclockwise from the read pointer to find the earlier samples. Counterclockwise corresponds to the index going down. Therefore, the answer here is that we're looking for gdelay buffer of 49. What, on the other hand, is 2 samples older than gdelay buffer of 1? Well, we know that the answer can't be -1. The actual answer is gdelay buffer of 99. Why is this the case? Well, by illustrating this buffer as a circle, we saw that once we reached the beginning, we could simply wrap around to the end and carry on counting to find older samples. On a similar vein, what is 5 samples older than gdelay buffer of 0? In this case, we'd also have to wrap around, and we'd find the answer is gdelay buffer of 95. Or, finally, how do I find something that's 100 samples older than gdelay buffer of 10? This one's a trick question, because there's only 100 samples in the buffer in total, and if we have gdelay buffer of 10, there's only 99 other samples stored in there. If we needed something 100 samples older than that, we'd need to have a larger buffer. From these examples, you might get an idea for a more generic way of doing this calculation. It involves what's called modulo arithmetic. Let's talk about that now. In C-like languages, the modulo operator is given by the percent sign. Modulo is defined to be the remainder after division, so after we've divided x by y, how much is left over? If x and y are both positive, then the range of the modulo output is between 0 and y minus 1. For example, if we took 5 mod 2, the largest integer multiple of 2 that fits inside of 5 is 4. The remainder after that is 1, so 5 mod 2 is equal to 1. Modulo arithmetic is extremely useful for completing the circle in our circular buffer, because it lets us always stay within the right range of array indices and wraps around the index when it falls off the end of the buffer. How do we do this then? Specifically, what value should we use for y in the modulo expression above? Well, we'll find out that if we use the buffer size as our value of y in a modulo expression, then what's left over is always going to be between 0 and the buffer size minus 1, which is exactly what we want for accessing an array. So in this case, we have an expression like gdelay buffer of n plus 2 mod 100, This will always give us 2 samples later in the buffer than n, even if n was equal to 98 or 99. A similar idea might be to do something like this, if we wanted 2 samples earlier to take n minus 2 mod 100. But there's a small problem in this case. The problem is that in C and C++, if the first argument to modulo is less than 0, the output will also be negative. So for example, minus 5 mod 2 is equal to minus 1. This is obviously not going to help us because we want a range between 0 and the length minus 1. Another annoying problem is that this behavior is also language dependent. Not every language implements modulo in the same way that C does. So the most robust solution is going to involve always adding one or more multiples of the buffer size like this. The expression looks a bit complex, but it's easy to unpack. If we wanted index n-2 in a circular buffer context, we first add the buffer length. Then we take that whole expression and we take the modulo by the buffer length once again. This means that even if n is equal to 0 or 1, we'll still end up with a positive valid index at the end of it. It's worth committing this expression to memory because it comes up quite frequently when you deal with circular buffers. Our second coding task then is to change the length of the delay. I don't want you to change the length of the circular buffer, leave that at ½ second, but I want you to use modulo arithmetic so that the delay that you get is only 0.1 seconds rather than the entire length of the buffer. It's worth considering how you would convert a 1/10 of a second into samples. You might even do that inside of the setup function. Pause the video here and see if you can get this shorter delay working. Okay, so here's our result. As before, we have a circular buffer and a right pointer. I've also added at the beginning a variable to keep track of the offset in samples. This is really just for convenience, so we don't have to recalculate it every time. I'm calculating the value of g offset inside of setup to be a 1/10 of a second. Then, inside of render, we have this expression to get the output. You can see our formula from before, which is inside of the square braces to read g delay buffer. We take the right pointer, we subtract the offset, we add a multiple of the buffer size, and then we take the modulo by the buffer size. This will always return a value between 0 and the buffer size minus 1, as long as the offset is no longer than the buffer. The rest of the code is largely the same, and we'll write it to the output as we did before. And here's that code in action. We can run it to hear the shorter delay. Let's move on now to consider a slightly different syntactical approach that can sometimes be cleaner. We discussed how you can use modulo arithmetic to look backwards from the right pointer to find earlier samples. In the example we just saw, we did this calculation every audio frame. An alternative approach to doing this calculation every time would be to use a second pointer or read pointer to keep track of where we're reading from. Then, every single audio frame will increment both the right and read pointers and wrap them around when they get to the end of the buffer. If we do this correctly, the read and the right pointers should move at the same speed and the delay should remain constant. In this case, it's the distance between the two pointers, rather than the overall size of the buffer, that determines our delay. Let's look at this in action. If our right pointer is located here, pointing at the oldest sample in the buffer, our read pointer might be located 8 samples earlier. What we can do is we can always read a sample from here, send it to our output, while we overwrite the next sample at the right pointer. So when x of 24 comes in, it replaces x of 0. We increment our right pointer, but we also increment our read pointer at the same time. They remain 8 samples apart. Then we replace x of 1 with x of 25, reading out x of 17. We increment both pointers again, replace x of 2 with x of 26, reading out x of 18, and we can go on like this indefinitely. Notice that as before, there's nothing special about the beginning or the end of the region in memory. It is effectively a circle. Our system therefore has 3 components at this point. We have our region in memory, or array, which we implemented as a C++ vector. We have our right pointer, which keeps track of where new samples will be written. And we have our read pointer, which keeps track of where we read the old samples from. In code, it might look something like this. The trickiest bit of getting this right is to figure out how to initialize the right pointer and the read pointer. The distance between these two pointers determines our delay. If we start our right pointer at 0, we have to figure out where our read pointer might go. I'll leave this as an exercise for the next task. Once we've done that, we can always read the sample from the read pointer, incrementing and wrapping the read pointer. Then we can write the current input sample using the right pointer, incrementing and wrapping that pointer as well. That brings us then to the next task. Keep the delay at 1/10 of a second, but rather than doing modulo arithmetic every single frame, use a read pointer in addition to a write pointer. You'll have to initialize the read pointer inside of setup to be exactly 1/10 of a second behind the write pointer. Here you might need to use modulo arithmetic as you did before. Pause the video and try that. Here's how we implement the result with a write pointer and a read pointer. First, we have to declare both the pointers as global variables at the top of the file. Inside of setup, we have to calculate the difference between the write pointer and the read pointer. We're using the same modulo arithmetic expression that we did in the previous example, but we're doing it only once inside of setup. Now you might reasonably ask, wouldn't it just be simpler to move the write pointer ahead and leave the read pointer at 0? This would in fact produce the same distance between the two pointers. The reason I'm showing it this way has to do with how some of the future examples will go, where we need to move the pointers around dynamically, and we'll find that it's more convenient to do it this way than the other way. We can move down into the render function, and we can see that reading from the buffer has become considerably simpler. All we do is read at the read pointer, and then we write at the write pointer as we did before. We now have two pointers to increment and wrap as we did before, and we write the output to the left and the right channels as we did before. So let's run this code now. Good, we hear the same delay as before. To make the circular buffer a useful delay effect, we might want to be able to adjust the delay in real time. So as we know, the delay time is given by the difference between the read and the write pointers. Therefore, if we want to change the delay time, we need to change the distance between them. We could do this by either moving the write pointer or moving the read pointer. Which way should we do it? I propose to you that you should move the read pointer. What might be the reason for that? The reason is that by moving the read pointer, we can keep the write pointer always moving at a constant rate. This means that we're always writing our samples into the buffer in a predictable way, and the circular buffer always holds the last n samples of audio. By moving the read pointer back and forth, we can decide which of those samples we want to read at any given time, but the contents of the buffer are much cleaner. On the other hand, if we had moved the write pointer, we might end up with a gap in the buffer where there are some samples that had never been written, or had been written twice in succession. If we want to implement a changing delay like this, we're going to need to use modulo arithmetic as before. Every time we get a new value of delay, we'll use this to recalculate where the read pointer should be with respect to where the write pointer is at the immediate moment. And that's your task for now. This task uses the GUI sliders, which we first saw in Lecture 4 of this series. You need to include the GUI and GUI controller libraries to do this. You'll need to create some objects and initialize them inside of setup. You should make your code have one adjustable GUI slider, which is a delay which ranges from 0 to 0.49 seconds, recalling that 0.5 seconds is the total length of the buffer. The delay will be given in seconds, and when you read it, you'll need to convert that into how many samples of delay are needed. You'll then use that value in samples to update the location of the read pointer based on the current location of the write pointer. One helpful hint is to make sure that you always check the edge cases of your code. In this case, check the edge case where the delay is equal to exactly 0. You should find that that produces, in fact, 0 delay and doesn't produce a delay of a half a second. What will make the difference here is which order you do your reading and writing. Pause the video here and make this adjustable delay work. Here's the example with the GUI libraries integrated. Remember that we have to include these two header files in order to use these libraries. There are quite a few more libraries than just this on Bela, and you can always find them by going to the Libraries tab of the IDE down here. To use the GUI, we also have these two objects, GGUI and GGUIController. This works as before. We can see inside of render that we are initializing these the way we typically do, and that we're creating one slider which has several arguments. We call it delay. It has a default value of 0.1 seconds, a range between 0 and 0.49, and no fixed increment, which means that it can take any continuous value within that range. Inside of render, we start at the top of the function by getting the current slider value. We store that in a variable called delay. This, of course, is measured in seconds, so we need to multiply it by the sample rate if we're going to get the delay in samples. Then we're going to update our read pointer according to the current location of the write pointer. This is precisely the same modulo arithmetic formula we've now seen several times. You might wonder whether updating the read pointer all the time could cause the delay to jump if we're not touching the GUI. In fact, if the value of delay hasn't changed, then this calculation should return exactly the same result for read pointer that it would have had anyway. Then inside of the for loop, we have the code similar to what we had before. However, one change is that we've moved the writing of the sample to be before the reading of the sample. The reason for this is that when gRead pointer is equal to gWrite pointer, we want to have the delay be equal to 0, rather than having gRead pointer read the very oldest sample inside the buffer. Otherwise, this is largely the same code that we saw before. We can run this project, and we'll hear it initially start out, as it usually does. Now we can open the Bela GUI. And we can use this to change our delay time. You can hear for very short delays that we have a sort of slapback effect. And for zero delay, it disappears back into the original sound. At this point, we've created a simple adjustable delay. The output is equal to the input delayed by n samples, which is what this expression z to the minus n means. The delay is the basis of a number of classic audio effects, the simplest one of which is the echo. The only thing we have to do to get an echo effect is to add feedback to our delay. This is also sometimes called regeneration. What we're doing is we're feeding a fraction of the output value back into the input of the delay line, so that the input to the delay is not just equal to in, it's equal to in plus f times out. F has a particular range of valid values. Can you predict what they might be? The minimum meaningful value is 0, which means there's no feedback at all. The maximum value is something just less than, but not strictly equal to 1, for example 0.999. If the value of f was greater than or equal to 1, then the echoes would grow in amplitude without bound and eventually would saturate our system. As a final task then, add feedback to the project that you just worked on to create an echo effect. In addition to adjusting the delay, add a second GUI slider which lets you adjust the amount of feedback. You might find in implementing this expression that you once again have to change the order of reading and writing to the delay line. Your code in this case doesn't need to handle a delay strictly equal to 0. That would produce what's known in signal processing as a delay-free loop, which can produce quite mathematically complex systems. Instead, you could set a minimum delay to be something quite small, say 0.01 seconds, or even a bit smaller than that. Once you build this effect, try various settings for the delay and the feedback, and try in particular the very small values of delay to see what that sounds like. Pause the video here. Okay, this code now implements adjustable delay with feedback. Notice that I've changed the minimum delay from 0 to 0.01 for the reasons we discussed earlier, and I've added a second GUI slider which controls the amount of feedback. Its default value is 1/2, but it can range from 0 to 0.95. If we now go down to render, we can see that I'm getting the value of the feedback slider and storing it in a float called feedback. The main change from this point is what we store inside the delay buffer, which is this line of code right here. gDelay buffer of gWrite pointer is equal to in plus out times feedback. In other words, we're storing into the delay buffer our current input, but also some fraction of the output, which is a delayed version of the input. We increment our pointers and wrap them around like before, and we write them to two different channels like this. We can run this code now to hear what the delay and feedback sounds like. Here you can hear a bit of a recurrent echo, and let's play around with the settings. We could turn the feedback up. Of course, this can saturate the system if the feedback level is too high. And of course, at 0 feedback, it just reverts to the original slapback. We can also change the delay time. Now something interesting happens when the delay becomes very small. And we can actually accentuate this by increasing the feedback. What's happened there is an effect called comb filtering. Essentially, we have multiple copies of the signal in quick succession, such that some frequencies are emphasized because they line up in phase, other frequencies are out of phase so they cancel out, so the result is something that sounds like it has a pitch. The frequency of the comb filter ends up being the inverse of the delay time. Besides echoes and comb filtering, it turns out the delay is the basis of rather a lot of different audio effects. For example, by changing the speed of the read pointer to move periodically faster and slower than the write pointer, we can bend the pitch of the signal and create a vibrato effect. We can mix that signal in with the original to create a chorusing effect. The flanger is also a delay-based effect, very similar to the chorus, the main differences being that it typically uses a shorter amount of delay than the chorus, and that the flanger sometimes also uses feedback. Each of these effects could be built on the same circular buffer machinery that we just saw. In addition to that, they'd need to use fractional read pointers, which we saw in Lecture 3 when we were dealing with wavetables. They would also require an LFO, or low-frequency oscillator, to periodically change the amount of delay. We covered those in Lecture 6. So this is something that you might try on your own based on what we've covered here. If you want more detail about the theory behind these effects, you can see the textbook that I co-wrote with my colleague at Queen Mary, Josh Rice. And that's it. As always, keep in touch with us, and we'll be back again soon with another lecture. For those of you who are watching this series as it's coming out, I'd also like to invite you to give me some feedback. In the video description is a link to a short survey. You can complete it anonymously, or you can give us your email address to be entered into a prize drawing. Thanks again for following along. We'll see you the next time.